In this video, we are going to talk about functions and relations, and everything we say in this video is totally consistent with what you know about functions from algebra. However, we do take a different perspective, and that we look at the functions and relations perspective from a set theory point of view. So this is the one kind of overview slide. There are many other slides with examples and discussion, and then at the very end of this video, there are 5 problems for you to try for review. We start with the definition of an ordered pair, and it is totally consistent with what you know of ordered pairs from algebra and graphing, like when you graph the ordered pair xy. And the ordered pair is a set whose members are some element A, and that corresponds to this first element of your ordered pair, and the set AB, so that corresponds to the second element of your ordered pair. In other words, the second element can be the same A as the first element, or it could be a different element. So another way of expressing that is that the ordered pair AB is equal to some element from set A, comma, some element from a set AB. And kind of written out, so your first element is from this set, A. So your first element has to be A. But your second element it comes from this set AB. So it either can be the same element as your first element, or it can be a different element. And there's this theorem that says that ordered pairs are equal if the first element is equal and the second element is equal. I have 2 more definitions, and then we'll do some examples. And the first definition is of the Cartesian product. So if A and B are sets, then their Cartesian product, or also called the cross product of A, B, written A cross B, is the set of all ordered pairs AB such that A, the first element, is a member of the set A, and B, the second element, is a member of set B. Another way of writing this is A cross B is equal to the ordered pair AB, such that A comes from set A and B comes from set B. The second definition is of a relation. So if A and B are sets, a relation between A and B, and we'll denote that with a capital R. If I were writing this, I'd probably write kind of a fancy script R, is any subset of A cross B. So we say an element A in the set A is related to the element B in the set B, if AB is in the relation, or the set R. And we denote this by writing A is related to B. If B is equal to A, we speak of R, a subset again of A cross A now, as being a relation on A. And now we'll do some examples. Let's say A is the set containing the elements 1, 2, 3, and B is the set containing the elements 4 and 5. So A cross B, that's all the ordered pairs where the first element comes from set A and the second element comes from set B. So let's start by combining the first element in A, 1, with everything in B. So that would be 1, 4, and 1, 5. Then we'll go to the second element, 2, and combine it with 4 and 5. So we have 2, 4, and 2, 5. And then last, we have 3 combined with 4, and then 3 combined with 5. So this is A cross B. Then we can define our first relation, and I'll denote this as R with the subscript 1. It can be any subset of A cross B. So I might just randomly choose 1, 4, and 1, 5. R2, I might just randomly choose 2, 5, and 3, 4. You can choose one element, you can choose all 6 elements, but any subset of A cross B defines a relation. And here we would say that 1 is related to 4 and 1 is related to 5. In R2, 2 is related to 5 and 3 is related to 4. A second example now uses intervals. So A is the set of numbers between 1 and 4, including the number 1 and not including 4. So I have that graphed here. A goes from the interval 1 and to 4, but 4 is open. In other words, we don't include 1. And then we have the set B is the half-open interval, open at 2, closed at 4. So I kind of put this soft bracket to mean we don't include 2, but we do include 4. And when I graph this cross product, I want everything including 4 and everything including 1, everything greater than 2. So I put this dotted line here to indicate we're not including 2, but everything above it. And here the 4, the dotted line, is to indicate we're not including 4, but everything below it up to 1. So this is the picture of A cross B. It's all the ordered pairs in this space. And you can see how I graph this on a Cartesian coordinate system, because we can interpret the points 1, 4, 1, 5 as points on a plane, which is why it's also called the Cartesian product. So if I wanted to shade what is in the Cartesian product, it's everything here, not included the dotted boundaries. A second example is if I have A is the half open interval 1, 5, B is equal to 1, 4, C is equal to 4, 7, and D is equal to 2, 5, and this is a totally open interval. If I want to sketch A cross B intersected with C cross D, and I want to show, just by sketch, not by proof, that that equals to A intersect C cross B intersect D. So for my next example, I have A is equal to the half open interval 1, 5, B is equal to the half interval 1, 4, C 4, 7, and D is the totally open interval 2, 5. And I want to sketch A cross B intersect with C cross D, and then I'm also going to sketch A intersect C cross B intersect D, and I'm just going to observe in my sketches that they are equal. So this isn't a proof, and the proof is something like what we did in the last video, but I will show you the sketch so you can kind of see visually what's going on. So we start with A cross B. So again, A cross B can be interpreted as ordered pairs in the Cartesian plane. So I'm going to sketch my interval A on the x-axis and my interval B on the y-axis. So I have A is equal to 1, 5. So here I have 1, and it's the open interval up to 5. And then B, I have the interval 1, 4, where 4 is open. I'm going to intersect that with C cross D. And again, C cross D are ordered pairs where the first element, the x element, comes from C, and the second element comes from D. So I'll sketch C on the x-axis and D on the y-axis. So C, I have 4, 7, open interval on the 7, and D is 2, 5. So now I can dot my A cross B. So I have A going from whatever it is, 1, 5, and then B is going from 1, 4. But I also have to make sure that my 1 is dotted, so that's this line, and my 4 line is dotted. So everything in this blue rectangle, not including the dotted lines, is A cross B. So I tried to indicate that with the color blue. And then next I have C cross D. So here I have C going from 4 to 7, and D going from 2 to 5, and the only line that isn't dotted is x is equal to 4. So in this green box, I have C cross D. And now if I want to show the intersection, that is this yellow region here, with the top and the bottom are dotted. The sides are solid. I'll do the same thing here for A intersect C and B intersect D. So now I'm going to do the intersections first before I do the crosses. So A intersects C, so I'm just going to look at this. It looks like it's this small area here, so I brought it down onto this graph. B intersect D is this small area here, so I brought it down to this graph, and now I'm going to cross them. So here I have my boundaries for B union intersect D. Here I have my boundaries for A intersect C, and I get this yellow region where the top and bottom are dotted, the sides are solid, and you can see that the two graphs are equal. And my last example, it looks A is equal to 1, 4, and B is equal to 2, 4. So that looks like this graph here, or these relations. And the relation A is related to B is given by A is less than B. So I start off by graphing the Cartesian product, which I just took from this graph here. but I want that A is less than B. So I took the line x equals y, or where A is equal to B, and I want everything where the x is less than B. So that'll be over here, right? Because I have numbers like 1, 4. So 1 is definitely less than 4. Over here I might have 2, 4. So I'm on the correct side of my line, and this is the yellow is my relation, A is less than B, where A and B are defined as these intervals. So now that we have the definition of ordered pairs and relations, we have this example which we had gone through, we can define something called an equivalence relation. So there are special relations that capture the idea of equality. So, when you have a number equals a number, you know what that equality means. But equality can be generalized. So you can talk about equality of sets or equality of matrices, equality of vectors. And the important properties of what makes something equal, and I put that in quotes, is one, an equivalence relation has the following properties. One, it's reflexive. In other words, everything is related to itself, or everything is equal to itself. Also, if x is related to y, then y is related to x. So you can think of, for an equivalence relation, that means if x is equal to y, then y is equal to x. That's the symmetric property. And last, we have the transitive property. If x is related to y and y is related to z, then x is related to z. So if you think of this as equality, if x is equal to y and y is equal to z, then x is equal to z. So these are three properties you're very familiar with from algebra, but now we're going to extend this idea to other things other than just numbers. So next I have some examples for you. So there's a couple of things to note in this definition. The first is for reflexive, this is a requirement for all elements x in S. So for every element in S, it needs to be related to itself. That is different from these next two properties, symmetric and transitive, because this one has an if in front of it. So what you want to remember about this is if x is related to y, then y is related to x. This if you have nothing that satisfies this pattern, where an x is different from y and x is related to y, if there's nothing that looks like 1, 2, for example, let's say everything looks like 1, 1, 2, 2, 3, 3. So there's if your relation has no ordered pairs where the second element is different from the first, so if it doesn't look like this, then it is automatically symmetric, because this part of the if is false. You don't have anything following this pattern. And so if this first part of a implication is false, then the implication is automatically true. I should warn you, I often abbreviate this first property, and instead of saying for all x and s, I just write this. X is related to x, and this is reflexive. And so you'll just have to remember that by this there's an implied for all x in S. I'm sorry, sometimes I'm just very lazy. The first example is the relation less than or equal to on the natural numbers. It's reflexive and transitive, but not symmetric. It is not an equivalence relation. So we'll go through each property one by one for an equivalence relation. So x is related to x. That's the reflexive property. So what I usually do is I rewrite x is related to x, but in terms of my relation here. So is x less than or equal to x? And the answer is yes. So it is reflexive. So the second property, if x is related to y, then y is related to x. That's the symmetric property. Again, I rewrite this in terms of my relation. So if x is less than or equal to y, is y less than or equal to x? And the answer is no. So it is not symmetric, which is why it's not an equivalence relation. And last, If x is related to y and y is related to z, then x is related to z. That's the transitive property, and I rewrite it with the relation. If x is less than or equal to y and y is less than or equal to z, is x less than or equal to z? And the answer is yes. So again, it is a transitive relation. Our next example concerns lines in a plane, and we want to consider one line related to another if they are parallel. And we want to know, is this reflexive, symmetric, and transitive? Which actually it is, but we will show that here. And since it is all three, it is considered an equivalence relation. So we have, is it reflexive? So is x related to itself? And I'm going to rewrite this in terms of my relation. Is x parallel to x? So a line x, is that parallel to x, to itself? And the answer is yes. So if x is parallel to y, then is y parallel to x? So if x is parallel to a line y, is the line y parallel to the line x? And the answer is yes. So it's symmetric. Last, transitive, if x is related to y and y is related to z, then x is related to z. So if x is parallel to y and y is parallel to z, is x parallel to z? And the answer is yes. Our next example includes the set of people living in Chicago, and we're going to say that A is related to B if A lives within a mile of B. And we're going to show that R is reflexive, symmetric, but it is not transitive. Therefore, it is not an equivalence relation. So x is related to x. That's the reflexive property. So the question is, does x live within a mile of x? And the answer is yes, so it is reflexive. If x is related to y, then y is related to x. So if we want to know if it's symmetric, we're going to ask if x lives within a mile of y, then does y live within a mile of x? And the answer is yes. Last, if x is related to y and y is related to z, then is x related to z? So in other words, if x is within a mile of y and y lives within a mile of z, does x live within a mile of z? And the answer is no. And I have this diagram here because y could live in the middle and x could live maybe 3/4 of a mile to the left, and z could live within 3/4 of a mile of y to the right. So it is not transitive. I have another set of examples, and on the next slide I have some solutions. So maybe this is a good one for you to pause the video, give it a try, and then you can look at the solutions on the next slide. Okay, we'll go through the first problem. If S is a set of all lines in a plane, then R is the relation is perpendicular to. So is it reflexive? In other words, is X perpendicular, using the definition of our relation, to X? And the answer is no. X is not perpendicular to itself. If X is related to Y, then Y is related to Z, substituting our definition of our relation. If X is perpendicular to Y, is Y perpendicular to X? And the answer is yes. Last, if X is perpendicular to Y and Y is perpendicular to Z, is X perpendicular to Z? And the answer is no, because X and Z could be parallel to each other. Then both X and Z will be perpendicular to Y, but they'll be parallel to each other. The second problem, S is a set of real numbers, and let R be the relation is greater than. Is it reflexive? Is X greater than itself? And the answer is no. Is it symmetric? If X is greater than Y, is Y greater than X? The answer is no. And then transitive. If X is greater than Y and Y is greater than Z, is X greater than Z? And the answer is yes. Last problem. Let S be the set of all triangles in a plane, and let R be the relation is similar to. So if you remember your geometry, this is easy. If you don't remember it like I don't remember it, it's still not too bad. Okay, reflexive. Is a triangle X similar to itself? Yes. If X is similar to Y, is Y similar to X? Yes. And then last, if X is similar to Y and Y is similar to Z, is X similar to Z? And the answer is yes. So far we've gone through the definition of ordered pairs, Cartesian product, and relations. We talked about equivalence relations and the properties, and we did these examples here. So our next topic is equivalence classes and partitions. So the first thing we're going to start with is a definition of a partition. So we can partition a set S, and it's a collection P of non-empty subsets of S. And this partition has satisfies two conditions. Each element of S belongs to some subset A in the partition. And two, for all A and B in the partition, if A does not equal to B, then A and B are disjoint. So an example, let's say our set is equal to the elements 1, 2, 3, 4, 5. And our first partition, so I made two partitions for you. Our first partitions can be the set A and B, where A is equal to 1, 2, and B is equal to 3, 4, 5. So let's see that this satisfies the definition of a partition. So P is a collection of non-empty subsets of S. So here we have 2, and they're non-empty, and each is a subset of S. And 1, each element of S belongs to some subset A in the partition. So we have 5 elements, 1, 2, 3, 4, 5, and 1 and 2 are in the set A, 3, 4, and 5 are in the set B. So everything in S belongs to one of the partitioning subsets. And 2, for all A and B in the partition, if A does not equal to B, then A and B are disjoint. So A and B do not have any elements in common. So you can see, so essentially what a partition does is it separates S into subsets such that everything in S goes into one of the subsets, and 2, the subsets are disjoint. It's kind of like what it sounds like, right? It's a partition. So here my partition for P1 looks like I've divided S into this subset and this subset. And then I did a second partition P2, and I put 5 into A, I put 1 and 3 into B, and 2 and 4 into C. So again, it satisfies the definition of partition. It's a non-empty set of subsets. Each element of S belongs to one of them, right? So 1 belongs to B, 2 belongs to C, 3 belongs to B, 4 belongs to C, and 5 belongs to A. So everything is accounted for, and that each of these partitions is disjoint from each other. So again, if we look at this partitions the set, I could draw it like this. A is here, and then B, this is my next partition, and then C is my next partition. So we kind of separate out our set. Okay, now that we've talked about partitions, we can talk about equivalence classes. And we're going to kind of work these definitions backwards. So we talked about equivalence relations. Remember, those are the relations that are reflexive, symmetric, and transitive. And they are sort of an abstraction of equality. So what an equivalence relation does is it partitions our set S. And it partitions our set S so that each partition is the set of things that are equal to each other. So that's kind of the idea. The partition kind of groups together everything that is considered equivalent or related. So related being the same. It's related, but it's an equivalence class, so they're kind of like equal. So this is our equivalence class then is a set, and we denote it with equivalence, a capital E, and then the lowercase x, whereas x is an element of S. So an equivalence class of x is equal to all the y in your set such that y is related to x. So looking at this definition, that means your equivalence class, EX, are all the elements in S that are equivalent to x. And that equivalence class is a partition. And then I'll go, since I worked everything backwards, starting at the top then, equivalence class and partition. So an equivalence relation R on a set S groups together the elements that are related. And we have this theorem, let R be an equivalence relation on a set S, then the equivalence class of X in S is a partition of S. So this kind of just summarizes the little pieces we've said here. Our first example of equivalence classes and partitions is on a set A. So A is a cross product. So the elements of A are ordered pairs where the first x-coordinate, the first coordinate comes from this set, and the second coordinate comes from this set here. So we're going to define a relation R on A, and it's going to look something like one ordered pair is related to another ordered pair, and then we're going to define the relation. So this relation looks a little different than before because we used to have something like A is equal to the set, and there would just be a set of numbers. And then we would say things like 1 is related to 2, or we would say like 1, 2 is in our relation. That's what our previous examples look like. Now our examples look like 1, 2 because is related to, let's just say 3, 4, because now we have a relation on A, which is a cross product. So our elements of A are ordered pairs. So we're going to talk about ordered pairs being related to ordered pairs. And so in this case also, I should go ahead and say that, so this is what we would say, this pair of ordered pairs is in our relation. I've given you a sense of why this is a little bit different. This relation is different from the ones we've seen previously, and it's because we're defining the relationship on A, whereas A is a cross product. So I have written out A here. So again, the cross product means we take every ordered pair where the first element of the ordered pair comes from this set, and the second element of the ordered pair comes from this set. So 1 pair as the first element, paired with everything in this second set. And then 2 as the first element, paired with everything in the second set. And I've done this all the way through. And I wrote this in a matrix form because it ends up becoming very useful to be able to see it this way. And this is also a very convenient table for you to use if you ever do probability and you're rolling 2 dice. But anyway, this is the matrix form, which I like to put this kind of cross product in. Next, I've gone ahead and defined a relation on A. So I said that x1, y1 is related to x2, y2 if x1 plus y1 is equal to x2 plus y2. So I rewrote that here. And looking at this, I can say that 3, 2 is related to 4, 1 because by the definition, 3 plus 2 is equal to 4 plus 1. I have 3, 1 is equal to 1, 3 because 3 plus 1 is equal to 1 plus 3. And then 6, 2 is related to 5, 3 because x1 plus y1, 6 plus 2 is equal to x2 plus y2, 5 plus 3. And now I can go through and see if this is an equivalence relation. So is it reflexive? Is x1, y1 related to itself? And then I plug in my definition of my relation to answer this question. Is x1 plus y1 equal to x plus 1 plus y1? And the answer is yes. I continue. Is it symmetric? So if x1, y1 is related to x2, y2, is x2, y2 related to x1, y1? So I plug in my definition of the relation. If x1 plus y1 equals x2 plus y2, is x2 plus y2 equal to x1 plus y1? And the answer is yes. And last, transitive. If x1, y1 is related to x2, y2, and x2, y2 is related to x3, y3, is y1, y1 related to x3, y3? Plugging in the definition of my relation and restating this, that's if x1 plus y1 equals x2 plus y2, and x2 plus y2 is equal to x3 plus y3, this should be y, is x1 plus y1 equal to x3 plus y3? And the answer is yes. So this is an equivalence relation. So we've established this is an equivalence relation, and now we're going to look at the equivalence classes. And this is where this matrix form comes in handy. And again, this is good for probability too. So what I've done is I've drawn these diagonals, and the thing about these diagonals is that's where the ordered pairs add up to the same number. So here on this diagonal, everything adds up to 2. On this diagonal, my ordered pairs add up to 3. On this diagonal, my ordered pairs add up to 5. So remember, my equivalence classes are groups everything that are equivalent. So this equivalence relation groups everything that adds up to 2 together, groups everything that adds up to 3 together, everything that adds up to 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I can say my equivalence class of 1, 1, also equal to, denoted sometimes with this bracket, that's equal to the set 1, 1. There's only one ordered pair in this equivalence class. So the equivalence class of E11 is a set containing the ordered pair 1, 1. My equivalence class E21 is equal to the set containing 2, 1 and 1, 2. So it's this here. It contains 2, 1 and 1, 2. So that's my equivalence class. 2, 1 is the set containing the ordered pairs 2, 1 and 1, 2. Also note, I could have, I wrote that here. So I used 2, 1 to denote this class, but I could have used 1, 2. It doesn't matter which representative element you want to take. Just choose one of the representative elements. Similarly for E31, those are the things that sum to 4. So I could have chosen E31, or I could have denoted this as E22, or I could have denoted this as E13, but it's essentially these elements here. And you can go on down, and I listed out all the equivalence classes here. And you can see that the equivalence classes partition the set because everything in A in our relation is in one of these partitions, and all the partitions are disjoint. And if I wanted to describe the partitions, I would say the equivalence relation partitions A into sets whose sum of coordinates are equal. So that's kind of the description of my partitions. So our next example is let S be the set A, B, C, D, and E, and define the relation R, the ordered pair AA, the ordered pair BB, CC, DD, EE, and the ordered pair AC and the ordered pair CA. Is this an equivalence relation? If so, describe the partition determined by R by listing the pieces in P, the partition P. So first we'll show that this relation is an equivalence relation. First, it is reflexive. Is X related to itself? Is every X related to itself? And the answer is yes, because we have AA, BB, CC, DD, and EE. Those are all the elements of S. They are all in our relation. Next, is it symmetric? So when we have the pattern X is related to Y, is Y related to X? And the answer is yes, because we have an AC, and that's related to CA. And I guess technically I should also say that when we have CA, we also have AC. And then last, is it transitive? If we have X related to Y and Y related to Z, is X related to Z? So I'm looking for this pattern where the middle things are the same. So in other words, I have AC and CA. So these two in the middle are the same. They're the Y. So my X and my Z need to be related. So AA needs to be related, and it is in the relation. So this is an equivalence relation. So now to write out our partitions, we have, I guess I could call this P1 is equal to the equivalence class of A, and that is everything that's equivalent to A. Well, that includes A and C. The equivalence class, or the second partition, P2, is the equivalence class EB. That is everything that's related to B, which is B itself. P3 is going to be, we don't need an EC because this is, by the way, I could have also denoted this as EC. I could also have denoted this as the equivalence class of C. So that's already done. ED is just everything related to D, which is only D, and EE, the fourth partition, is everything related to E, which is just E. It's kind of funny since our last example was when our set was cross products, I kept wanting to write ordered pairs in here. But no, we're talking about everything that's related to the element A. Remember, S is now just simple elements. It's not ordered pairs. So this is the complete answer. So here are 5 review problems for you to try. Pause the video, give them a try, and then I will have solutions on the next slides. Here's my solution for problem number 1, and you'll see that I use the definition of this x means cross product. Here's my solution for problem number 2. Here is my solution for problem number 3, and I also wrote out the partitions here because it was an equivalence relation. Here's my solution for problem number 4. And my solution for problem number 5. And that's it for this video. Thank you for watching.